Next talk is from the folks who brought you Hipparcos and then Gaia. Now we have Gaia number 3, the sequel, and what will we do in the infrared? And David Hobbs will give a talk on that.
Okay, thank you. Yeah, it's good to reset the clock. Thank you. Okay, hi, I'm David Hobbs from Lund Observatory in Sweden, and I've been working on Gaia for the last 15 years, mostly in the core astrometric solution for Gaia. But I've been distracted in recent years by thinking about what we should do in the future a little bit. And what we've come up with is this new project called GaiaNIR. It's a very obvious name, but we're going to give it a nicer name at the end of the talk. You can see exactly what we're doing from the name. And our intention is to probe the hidden regions of the galaxy that Gaia cannot reach, but we will also do a complete astrometric survey of the galaxy, just like Gaia. So a few years ago, we were thinking about which directions we would actually go in with new astrometry missions. And one of the obvious ones, the one that I have picked, is a Gaia-like mission, but going into the infrared. But there are other options as well. Daisuke has just given a talk about pointed relative astrometry in the near infrared with the small Jasmine mission. We also considered doing kind of a giant Jasmine mission as an option if we didn't have the correct detectors. Daisuke actually said that near infrared detectors cannot integrate light in the way CCDs do, and he's generally correct, but we have found a way around that now. There's also other people proposing pointed relative astrometry missions, and I think we might have a talk on that later on as well. These are missions like SIM, which was here in the US, which eventually got cancelled. It evolved into something called NEAT in Europe and then into TIA in Europe, and it's still being proposed today. So we might see more about these. These are ultra accurate missions aiming at nanoarc second astrometry, and very interesting to answer specific questions on dark matter and also looking for exo-Earths with these. And there's a lot of overlap between these. I don't think we're all in competition with each other. We're all very complementary, doing things slightly different, and we'll see how things work out in the future. Now, for GaiaNIR, we have 3 main science cases. I'm not going to go through them in a lot of detail today, but I have extra slides on them here. The first obvious science case is that we're going to go into the infrared, and then we can do astrometry and photometry in these hidden parts of the galaxy. This is something that Gaia cannot do very well. It can't point towards the central regions of the galaxy, like the bulge bar region, and really measure everything. It's obscured by the dust in these regions, and that gives this new mission a real objective. And I think this is one of the most important objectives that we have in the mission. I'll show you a little bit more about that in a few minutes. Another thing that we can do with this new mission, because it's also an all sky survey with similar accuracy to Gaia, we can actually, we have a 20-year gap between the 2 missions, at least in my nominal estimates. And if we combine the proper motions, the positions of the stars from these 2 missions, then we can get improved proper motions of these stars. And that will give us proper motions that are something of the order of 20 times better, depending on exactly when we launch the new mission. That's compared to DR4, which you haven't even got yet. It depends what you compare with, what these numbers are. But that will actually push the accuracy of the mission just about into the nanoarc second regime for proper motions only. It's not very far into the nanoarc second regime, but we can still perhaps claim that. And then the other big science case that we have, we just had a talk by Francois Mignard, and he showed a picture of the quasars in the galaxy and the huge big gap in the galactic plane where we don't have many quasars. We can at least help with a near infrared mission. We can extend the reference frame into the infrared, and we can fill in at least some of this gap, probably not all of it, but some of it. And we can also reset the reference frame and the Gaia catalog, because there was a question about the accuracy of the Gaia catalog. It will decay over time. Francois showed a nice plot on that. But if you also include, if you have a joint solution between Gaia and the new mission, then the Gaia catalog will be maintained for a much longer time. And I can probably quickly show that graph in a few minutes. So here's the kind of schematic outline of the mission. You can see, maybe I should use this giant mouse. Yeah. You can see here is the Gaia mission over here. It started in 2015 to 2025. Then we leave a big gap of 20 years, and then we could launch a new mission in 2045, which would run to 2055. Even the launch is beyond my retirement time. So I'm really excited to be here with a young group in this audience who might actually see the results of this mission. Of course, if we shift the launch date 5 years earlier, then we get worse astrometric accuracy. We probably wouldn't get down into the nanoarc second regime. The numbers here for proper motions are 800 and 700 nanoarc seconds per year. So we're just about getting in there. If we push the launch date even further out, that would be even better, but we'd probably all be dead. So it's not very useful for us. So this is a balance between being alive and dead or retired. And I picked the retired option for me. So this is all very exciting. So it really does give excellent proper motions. And this we get for 2 billion Gaia stars, basically, this combination of catalogs. The near-infrared science cases we will get for something like 10 billion new stars on top of the 2 billion that I'm mentioning here. So these are really extraordinarily large numbers, but still only 5% of the galaxy, right? So we shouldn't think we're finished when we finish this mission either. So this is just a graph to show you what we actually see. So the detectors, the infrared detectors, have cutoffs of 1.8 microns or 2.5 microns generally. And we did calculations with galaxy models for both H-band and K-band cutoffs corresponding to these. And we found that we would get 5 to 6 times more stars depending on where the cutoff is. I think we should go to the K-band cutoff and get 12 billion stars in total. That's a huge number of stars. As I said, it's still only 5% of the galaxy or so, but the other thing we found were the extinction models. We tried a few different extinction models doing these calculations, and we got different answers, which means that we don't fully yet understand how many stars we're actually going to see, and we may get surprises. But the newer extinction models are the ones I'm quoting you here, and I think they're the better ones. But this becomes a science case in itself. I think that's very interesting as well. We shouldn't be relying on models anymore. We should be out there measuring the stars and finding out how many are really there. I've now got 3 slides, which I'm going to not go through here, outlining the near-infrared science cases, the improved accuracy science case, where I'm going to stop very briefly on exoplanet science, because Gaia can detect exoplanets with periods up to about 10 years, plus or minus a small amount. But with the new combined baseline, we can go up to periods of 40 years for exoplanets. And that's by combining Gaia and the new mission together. But we will also be able to detect exoplanets in the nearby star-forming regions that Gaia can't detect. And this is very exciting as well. So we will also get new, not just improve the accuracy, but we will also get very new objects. And with the longer baseline, we will also find new objects that couldn't be fitted with Gaia, but maybe were seen by Gaia. It's very important that we have the support of the exoplanet community. And I think this conference here, or this workshop, has shown how important Gaia has been for the exoplanet community. And I think this new mission can also be that. So I hope you will support us in this and also get involved in this a lot. I'll skip over this. This is the reference frame, the plot that Francois showed earlier, where he showed the decaying of the Gaia catalog. This is what happens if you combine the 2 missions. Instead of having 100 milliarc seconds up here on the y-axis, you recover 5 milliarc seconds. It means the combined catalog will last for maybe hundreds of years, whereas the current catalog will decay over the next 50 years significantly. And that's important. Now people are always asking, what is the big science question that we're going to have? And I think it's very clear. It's the hidden regions of the galaxy is where the big discoveries will be made. And particularly this region around the bulge in the bar. Daisuke also mentioned that in his talk, I think. But we can do a much deeper, much longer wavelength survey of this region. And it is a survey of the whole sky. So this region will be completely covered. I put in some pictures here of, one is on the left is the visible picture from the Hubble Space Telescope. And the other picture is a new picture of the same region with James Webb. And I think these pictures show very beautifully exactly what's going to happen when you go from visible to the near infrared. This is the same, roughly the same wavelength band that we're suggesting. And you can see A small number of stars in the Hubble picture, and then you see you see hundreds or thousands of stars suddenly appear in the James Webb picture. We can measure those stars with the new mission, and that's profoundly important because we can do this all the way towards the galactic center, towards star-forming regions that are all obscured for Gaia. And this is really quite exciting that we can do this kind of thing. So I think that's one of the most important takeaway science cases, although we have a huge range of different science cases as well. And now I want to pose a provocative question. Can we also get the radial velocities of these stars? And I'll come back to that a little bit later in the talk. So we've been doing a lot of work with white papers since 2016. We started proposing this mission to ESA. And we were lucky to be selected as one of the first missions that ESA actually did a study on. And they took us into a room with 40 specialists in spacecraft design, and they sat us down for a couple of months. And we designed a whole space mission, which looks at first glance very like Gaia. And from their point of view, they were able to figure out how much it would cost to build this thing, which is very important. We also wrote Astro 2020 science papers, more so to awareness in the US about this project. And we also submitted the equivalent to Voyage 2050, which is the European equivalent of Astro 2020. We submitted a science paper there, and the results of that came out very recently. I'll show very quickly what they said. Basically, they picked their #1 candidate to be an exoplanet mission that may host life. And this is the life mission that was mentioned in the first talk this morning. And that's being given #1, but they add caveats to this. And the caveat is if it can be achieved in a feasible and affordable mission. And that's a big if, unfortunately, because flying interferometers are very expensive. I think it can be achieved. Certainly it's feasible. But is it affordable? We have to see. And so they say then if this is not the case, then they want to do a large mission on the hidden regions of the galaxy. And we had actually proposed our mission to be a medium class mission, but it turns out that we cost something like 800 million euro, which is a large mission basically, but we're safely within the large mission window. So I think from that point of view, it's very good. Now, Astro 2020, of course, is proposing to do a 6-meter class exoplanet mission. So there's a lot of talk about what Europe will do, and a lot of people feel that it's very likely that Europe will go with the American mission and not actually build a separate mission itself doing similar things. We don't know if that's true or not. It's just a hunch, but we're hopeful that that will open our window, but if we're not selected as a large mission, we're going to propose this as a medium class mission anyway. So we're not really in competition. The politics we have no control over. So here's the design. I won't go into it in a lot of detail. At first glance, it looks just like Gaia. Especially from the outside, it has 2 telescopes, 2 fields of view. The main difference in the new design is over here, we have 1 primary mirror instead of 2 primary mirrors, and we compensate for that by having these 2 flat mirrors at the entrance pupils in order to get the 2 telescopes to work. And then we have a similar kind of arrangement as Gaia with the focal plane and so on. And here at the end is the focal plane array, which I want to go into in more detail. But Daisuke brought up this problem about detectors. When we started this work, we didn't have detectors that would integrate the light. Because we're a rotating mission, you have to integrate the light as a function of time as the stars pass over the detectors. CCDs can do this, they can transfer electrons, but mercury, cadmium, tellurium infrared detectors cannot. They can't transfer the electrons. But we have found a solution to this. There's a small company in the UK that's been taken over by the Italian Leonardo. And they have what are called avalanche photodiodes, which are the equivalent, the modern solid state equivalent of the photomultiplier tube that was used on Hipparchus. And they have some very nice properties because you can read these things out thousands of times per second. And then in software, you can integrate the light effectively by stacking the images in the correct way. They have a very high TRL level, technical readiness level, and the Australian National University has been using them on ground telescopes, and they're planning to deploy one on the ESS for astrometry. So that will raise their TRL level even further, which is very hopeful if they get it onto the ESS. We have options. These detectors come in different wavelength cutoffs of 2.5 microns or 3.5 even. I don't think we should go to 3.5 microns. We will simply get too much crowding and blending in the galactic center. And there isn't really that many big science cases, I think, to go further than 2.5. So I think we will stick to this, and then we can avoid some of the crowding. We may still have crowding issues anyway. And another big problem is that we might see too many stars to actually download. That's amazing that we're bandwidth limited in this mission. And it's going to get worse. I'll show you in a few moments. Another problem with the detectors is they can't go below 800 nanometers. And that means very blue stars are not going to do well. But the number of blue stars is small in number, and we're really a red mission. So I think we can live with that. So here's a look at the detectors. This is what they have at the moment. This is only 25 pixels wide, and I'm not sure how many it is long, but they're very small detectors, and they can build them in different sizes with different widths and so on. And we have to talk to them about how to do this exactly. But basically, in order to produce one Gaia CCD, you have to have at least three of these objects with 1,000 pixels each and a 15 micron chip. If you have a bigger pixel pitch, then we need smaller numbers of stages. But this is all something now that we have to work out exactly how we build these detectors. But the point is that you can transfer the information from one individual detector into software, and then you can continue stacking them in software in order before you do the image parameter determination. So you can effectively make a large detector out of many small detectors using these devices. And they're relatively cheap, I'm told, but I don't know what that actually means. So moving on, then we have different options for different wavelength cutoffs. There is one that goes all the way from 0.8 to 2.5 microns, and it's probably this one that we will use, but we can also use the other options to make filter bands, if you like. But one of the most important about these APD detectors is that they have very low readout noise and very low dark current, which is very exciting. And I think this is, if it really holds true in lab experiments, this is a game changer for astronomy. And I'll show you why in the next slide, because I've done some calculations with suggested readout noise from the company. I'll show in a few moments. Here's the focal plane that we're planning. On the left, we have the Gaia focal plane. It's very large with all the astrometric field, the photometers, and the radial velocity spectrometer, and the sky mapper. What we've done in the new focal plane to save money is we've combined the sky mappers and the photometry all in one field. We do the astrometry, and we can figure out which field of view the stars come from by monitoring the motion of the stars across the focal plane, which they move differently depending on which field of view they come from. And also now I've stuck in, this is a new edition which we stuck in here this week, of a radial velocity spectrometer. We have to think about that. Can we actually afford this? As I said, we're bandwidth limited probably, so this could be an issue, but we should definitely try to do this, because an RVS spectrograph is the one thing that people continually ask for. It's for galactic dynamics super important. We've done end of mission calculations. I don't need to go through the details, but basically we put the flux from different types of stars at different magnitudes into a simulation. And then we pass that through a modulated transfer function, which mimics the whole telescope and the pixels and so on in the focal plane. And then we can calculate the end of mission accuracy. Here are the results. On the left graph is for Gaia. So I've reproduced the results of Gaia, and you get this typical behavior. You get about 22 microarc seconds per year, 22 microarc second parallax error at 15th magnitude. So I reproduced the results of Gaia, and you can see on the graph that it has this typical exponentially increasing error as we go to fainter magnitudes. And it ends up at 506 microarc seconds for the parallax accuracy at 21st magnitude. This is roughly what we expect from Gaia and what we've seen before. But now if we do the same simulation, but we assume the APD parameters, the new detectors, because of the very low read noise, the new APD detectors actually have a different behavior. This is a logarithmic y-axis here, but you can see it's linear on a logarithmic axis, which means it's only increasing logarithmically. And that means at 21st magnitude, we only have an error of 80 microarc seconds in the parallax. That's a factor of more than 6 better than Gaia. And that's profound. It's not the same for every type of star, it varies. In fact, on the next graph, I have a summary of the different types of stars. We've done it for the blue stars, turn out to be slightly worse, but that's completely expected because we have very little sensitivity for blue stars. Solar type stars are roughly the same as Gaia. But when we go to the red stars, moving up here, we get factors of 2.5, 2.2, 4.7, 6.3, and 2.7 better than Gaia. The one I showed you in the previous graph was this 6.3 result. It's the best result for a red, an M3 giant star. So we can outperform Gaia in the red. And this is surprising because we're going to longer wavelengths. So it's a little bit of a surprise, but because we have a very large bandwidth, we collect more photons, and some of those photons are also in the optical region, and that means that overall we get very good accuracy, even for these longer wavelength stars. So the big question I want to start thinking about now, and this has popped up in the recent weeks, is we had initially got rid of the radial velocity spectrograph because we thought it was too expensive. And we thought we couldn't do much better than Gaia, but now I think we can actually do much better than Gaia. And there's a number of reasons for that. One is that these new detectors have lower noise, which helps. It means we could possibly go deeper than Gaia with RV. But the other thing we can do with these new detectors and that we couldn't do with Gaia is we can change the scanning motion of the mission. So we can have the normal scanning law of Gaia for the first 2 years of the mission, and then we can slow it right down and focus on doing spectroscopy of stars. And we should maintain the same scanning law because when we cross the galactic plane, we're going to have so much data that we won't be able to download it. So we'll have to store the data on board. And then when we come out of the galactic plane, we can start downloading the data, and we're measuring roughly much fewer stars. And we can keep repeating this switching between fast scanning and slow scanning with these new detectors. This is a kind of a software controlled parameter. So it's not like with the CCDs where it's a clock controlled parameter. And that would mean that we could spend, as long as the last period is astrometry again, that means that we could go deeper. And also while we're doing the spectroscopic survey, we can also do deep astrometry as well, because we're integrating the stars for a much longer time. It means we can go deeper. So this gives us an opportunity to go both deeper for astrometry and deeper for radial velocity. We have to think more about this, exactly what it means, and do calculations about the data rates and so on, if it's really possible or not. But if it is possible, we could get a fabulous mission where we have a deep astrometry and radial velocity survey that goes well beyond Gaia. And I think that would be a game changer. But unfortunately, it's not going to be free. This is going to cost money. And complicate the spacecraft quite a bit. So we have to look into that and see exactly what it will cost us. But it's very much worth thinking about, I think. So that's a summary of this. So I've done these calculations, reproduced the Gaia results reasonably well, and then the improvements we've made is that we've modified the scanning parameters also to use the optimum ones, because Gaia was originally proposed with better scanning parameters, and then for various reasons they were changed. But I put them back in, and that helps improve the accuracy. The long wavelength range compensates for the longer wavelength. The bandwidth compensates for the longer wavelength, but the lower read noise of the detectors is the real game changer. This allows us to be even better, and we have to follow this up now with laboratory experiments to really verify that this really works as we're told it does. I think we shouldn't go to longer wavelengths beyond 2.5 microns. We should focus on going deeper rather than going to an even longer wavelength. I think we can get more science out of going deeper. And the combination of those improvements then can give better performance for most stars than for Gaia. But my final summary point is this idea of adding a slow scan rate for part of the mission and a spectrograph would allow a radial velocity survey. The biggest question there is, do we have the bandwidth to download the data? That's something that's going to be a challenge for us to do, but we have to work on that and see what can actually be done. And I promised a new name for the mission. I'm suggesting the Hera mission is the new name, because there's a very nice creation myth of the Milky Way from Hera, the goddess Hera. She was suckling the infant Hercules when she was asleep. Zeus had placed Hercules on her breast. And when she woke up, she pulled away and the milk spurted out, creating the Milky Way. I don't know, it's the nicest one I can come up with, but it's people, if you have other suggestions, please send them to me. And I've had one other suggestion so far, so not too many. Okay, I'll stop there. Thank you.
So thanks very much. We have time for one or two questions, and you'll kick it off. I guess the one concern I have is the longer wavelength, hurts you in a couple of ways, and you described how you buy back some of it. But I'm worried about the confusion aspects that, 21st magnitude in the galactic plane, there are a lot of stars per square anything. And I think you're actually going to really hit your limits for accurate astrometry at a much higher level. High latitude, of course, you'll do very well. But down at the, in the plane, I think, I'm worried you haven't taken enough account of the confusion.
No, that's completely correct. We haven't had time to study this properly yet, and it may be that we have to go less deep in the galactic plane when we see too many stars, and that's something that we have to study a bit more. But I think that might be a problem. I agree. So it looks good on paper, but in practice, we have practical problems.
All right. Hey, so this is really exciting. I'm super glad this might be happening. So as you were talking, I was wondering if there are any observations or science questions or something in particular that you would like people to focus on that would help with the decision making in the next 20 years about this mission.
Oh, yeah.
Yeah. What should I be doing to make sure this happens?
Yeah, I mean, I think we know a lot from Gaia about what we expect to see. So the real question is really what we see in the galactic plane part, and this is very tied together with his question. What can we really measure? Because if we do get these confusion limits in the galactic center region, then that takes away from our science cases a little bit. So we do have to look at that very carefully, and I'm not really sure what's going to come out of that yet. I think in Gaia also we suffer a bit in the galactic center, so it's a problem already with Gaia, and it's going to be a much bigger problem on this. But somewhat, I mean, we have advances in computers and so on, so we can store more data as we cross the galactic plane, because we cannot transmit it all instantaneously to ground. And that's why I want to maintain, other people have suggested that we should scan only the galactic plane. And I don't think that's a good idea, because we will just have too much data then. So I think maintaining the normal scanning law, crossing the galactic plane and so on, is better, because then we can store data and transmit it later. So that partially solves these problems, but doesn't get rid of the confusion issue either. So if you're interested in studying this first, we need people to start doing these kind of simulations of the galactic center to see what we can actually extract.
Cool, thanks.
One last question.
Okay, I just want to also express how excited I am at the potential of this as a brown dwarf scientist.
Yes.
Somebody that thinks these are the greatest objects since sliced bread. This is we need an all sky near infrared astrometric mission that goes deep. And so I want to offer up the brown dwarf community to you as a helpful aid in designing some science cases.
Yeah, I apologize. I skipped completely over the brown dwarf. They are mentioned, of course, in our white paper that was published in Experimental Astronomy, but I didn't have time to go into the science case, but there are fabulous science cases there for brown dwarfs.
Okay, yeah, I'm going to be happy to talk to you about this later too, because I can pitch you on about 100 of them. But one thing I didn't catch, and maybe you said it, was the colors that you were going to have as a yield from this. So you were saying it's H or K band, but is the H minus K color going to be the color?
I mean, this is also requires more study, but the way we intend to do things, the first filter band will see everything. Then the second filter band will see a narrower range, and then the third an even narrower range. So we have in the design 4 filter bands, but we haven't done any serious study of this yet either, if this is the optimum way to do it or not. So also, if people want to suggest better ways to do the filtering, then we're quite interested to hear about that. This project is only really starting up now, so it's kind of anybody who wants to get involved in it can come with interesting ideas, and we have to optimize all of these things and to get the best of the science out of it. So if you have ideas, by all means, contact me.
I got it.
So one question asking, how can an earlier launch decrease the proper motion accuracy?
Well, the longer the baseline is, the better for astrometry. So if we wait 200 years, we will get a fabulous long baseline, but we won't be around to do it. So it really depends on when ESA come with calls for new missions and we propose. So we will react to their calls and then put in proposals whenever their calls come out. But we know that space missions like this take about 15 years to build and get them launched. So that kind of puts a lower limit on it, and anything after that then is possible. We have to see. So it's not something I think it'll be 2045 plus or minus 5, I would say. And I can't control it very much. So.
Okay, well,